was 4 inches above the surface, and so they released it, dropped 4 inches, and obviously had no problem with that. That happened on Saturday, and it would have been early morning Mars time, because as we pointed out either last time or time before, when the helicopter dropped, that any contact with the rover, and in particular, it meant it couldn't get any more power from the rover. So its only source of power is this solar panel that you see up on top. And so they wanted to put it down early in the morning so it could sit out there all day and get its batteries charged as much as possible before that first night. So it was dropped, and then the rover, I say backed away. It may have actually gone forward and turned around. I'm not sure, but at any rate, it got away from the helicopter to give it, make sure it got plenty of sunlight on the solar panels. And then it went through Saturday night on Mars, getting its only heating from a little heater that it has. And we know that the temperature at night where it is gets down to about 90 degrees below 0 Fahrenheit. So that's pretty cold. And that would be too cold for some of the electronics on the helicopter. And so it has that little heater to keep them warm enough so that they will still perform. And so it's always necessary that its batteries be charged enough to run that heater all night long. So then on Sunday morning, they sent a command to the helicopter. And I think we talked about this before. Let's just review this. The way they get information to and from the helicopter is through the rover. And the way stuff gets to the rover is through the various satellites that orbit Mars. So when they wanted to make sure it was okay Sunday morning, they sent a command through this NASA Deep Space Network, went first to one of the satellites orbiting Mars, was relayed down to the rover, then relayed from the rover to the helicopter, saying, hey, run a status check and let us know what's going on. And so the helicopter ran a status check and then just reversed the process, sent the information from status check back to the rover. Rover sent it back to the orbiting satellite, which sent it back to NASA's Deep Space Network. And they found out, yeah, sure enough, everything worked just fine. And then I'm not sure it was that first day or not, but at some point then, they had of course, we've mentioned before, the helicopter has its own cameras. And so they got the helicopter camera to take a picture of the ground. And so this picture is actually taken by the helicopter. And you see first the ground, and actually, that looks, I know we said they tried to find the, smoothest surface possible. That doesn't look totally smooth. It looks kind of a little bit rocky. And so obviously they did an excellent design with the legs so that when it was dropped, it was able to sit there and not get it tilted over on some kind of angle or even fall over. But at any rate, it took this picture, and what you see up here at the top of the picture, those are the wheels of the rover. So it's the camera on the helicopter is facing back towards the rover. So what happens next? Let's go back a couple of plots to here. You can see here, that's the helicopter blades, and you can see they're still kind of curled up there. And so I think I've seen a picture that indicates this is already correct, they've already extended them so that they're in the working configuration. But I think what hasn't happened yet is the testing of the blades. I suspect that might be happening today, certainly by tomorrow. There's a two-stage of that test. In the first stage, they just simply basically turn the helicopter on and let the blades spin slowly for just for a little while, just to make sure that they're turning okay. That every and then they collect data from the helicopter indicating how it thinks that those blades are performing, and then they shut it off and they send that data again, gets sent back to NASA. And so that will, like I say, that might be happening today. I think it would certainly happen by tomorrow. And then that data gets sent back, and NASA checks it over and makes sure that everybody agrees that, yeah, the blades are working the way we expect them to work. And then they send a command to the helicopter to spin those blades at the full operational speed. Well, the full operational speed is 2,400 revolutions per minute. Now, I didn't know, I had to look it up. I was curious about how fast helicopter blades spin for helicopters down here on Earth. And it turns out they spin between 200 and 600 revolutions per minute, depending on the size of the helicopter. And it's kind of, it's a little bit backwards. The big helicopters have the slowest spinning blades. They run about 200 to maybe 300 RPMs. Smaller ones can run up to 600. But notice that's a big difference between, say, 600 RPM and 2,400 RPM. The reason why the Ingenuity blades have to spin that fast is because the atmosphere on Mars is just so thin. We mentioned before, the atmospheric pressure is 1/100th of what it is on the Earth. And the way helicopters work, basically, when the rotors spin, it causes a difference in the atmospheric pressure. The atmospheric pressure on the top of the blades becomes less, and the atmospheric pressure on the bottom becomes more. And that difference in the atmospheric pressure is what gives the helicopter its ability to lift up. And because the atmospheric pressure is so small to begin with, then the difference you're going to get on Mars between the top and the bottom is going to be a lot less pressure difference than what you get down here on Earth. And so in order to make up for that, they've got to spin the blades a lot faster. And we had a question maybe last week before, why design this special helicopter? Why not just send a regular old drone that you can go down to, well, I was going to say Radio Shack, but you can't go to Radio Shack anymore because they're not there. I guess you could go to, I don't know, get one on Amazon. Okay. Anybody can get a nice little drone that'll fly just fine down here. But it wouldn't work on Mars because, again, the spin of its blades is just not nearly enough to generate enough pressure difference for it to fly. So that's why the helicopter had to be specially designed for this purpose. All right, so and when they finished all the testing, the next thing that happens right now, and we'll see a picture of this in a minute. I said that the rover either backed away from the helicopter or maybe went forward and turned around, but it's pretty close to helicopter still. It's only about 5 or 6 feet away. But what's going to happen once they decide, yeah, we're ready, that we can try to fly this thing, then the rover is going to move off, and it's going to go to that point that we showed last time. Its viewing station, and that's about 60 feet away from the helicopter. Now, that's not quite as simple as it sounds. Say, okay, rover drives 60 feet away and we're set to go. Um, that would be, you know, if we had a person up there on Mars driving their rover, that would certainly be true, because a person would drive the rover the required distance, and then he'd easily be able to say, "Oh, there's a helicopter over there," and orient the rover so that the cameras were pointed directly at the helicopter. But we don't have a person up there. Okay, everything's got to be done by commands sent from down here. And that makes it much trickier to do this. What's happening right now is that the rover all day long, it's of course it's all taking pictures all day long anyway, because they want lots and lots of pictures of Mars. But particularly, it's taking lots of pictures of the area right around the helicopter. And the reason it's taking so many pictures of the area right around the helicopter is so that when after they have moved the rover away the required distance, when they want to orient it back to point directly at the helicopter, then they'll use the guidance software. It will review all those pictures it has that show where all the little rocks around the helicopter are, and it'll say, okay, I'm going to keep turning till I see one of those rocks. When it sees a rock, it'll say, now, okay, now there's another rock should be here. I'm going to turn till I see that. And in that way, by using some references of rocks that are close to the helicopter, the rover can manage to get itself oriented properly so that all its cameras have the best possible view of the helicopter. Now, the plan as of today is that the helicopter is going to try the first flight on Saturday. Now, I say Mars time. That means, you know, when it's Saturday on Mars, and that will probably actually be sometime early Sunday morning here. I haven't tried to actually work out the time differences, but I've noticed a couple of things, and also some information about when they expect results back indicate that the days are a little bit shifted between here and Mars. And that, of course, happens because the day length on Mars is 37 minutes longer than our day length. So each day, Martian days shift a little more from Earth days. So when I say it's going to fly on Saturday during Mars time, it'll probably actually be early Sunday morning here when that flight takes place. Okay, now this is the picture I was telling you about. It's kind of hard to see, but that's the helicopter right there. And here's the rover over here. So you see how far apart they are right now. Now, if you're like me, when you look at that picture, you say, wait a minute, who took that picture? You know, because there's nobody else up there, right? Just the rover and the helicopter. And that is indeed correct. But this is an example of, and we've seen the same thing. I'm sure if you followed the other rover, Curiosity, very much, you've seen this kind of picture from Curiosity, where you'll see a picture where it looks like somebody took it, because you seem to be seeing the entire rover and some stuff in the background. The way that's actually done, the robot arm here has this camera on the end, and it extends, as you see, it can extend out fairly far out, and it takes not a picture, it takes a whole series of pictures. And then the software, which is the same stuff we looked at a couple of weeks ago at a panoramic picture made from a lot of different pictures taken by the rover. That same software is able to make this kind of picture that seems to show us the entire rover as well as other stuff. There's not really a cameraman up there. It's just done by some very intricate software working on many, many pictures taken by a camera out here at the end of the robotic arm. Now, what else you can see here is you see the tracks made by the rover as it's maneuvered around from the time it put the helicopter down. Okay, now what we've got here,
Really clear.
this looks, hello, here we go. This looks like a video actually, but it isn't. It's again just a whole series of pictures shot by the various cameras, and then somebody just put them all together, and but you get a real nice. Here's a close up showing how the helicopter's sitting on the ground, and there you see. This is where I think the blades are extended fully. There's the solar panel sitting on top, and you notice all those little rocks down on the ground. They really, they're not all buried in the dirt. Some of them really do stick up. So as I said, it's an amazing feat that they're able to get those legs to properly stabilize the helicopter when they put it down.
Close.
But you do see there seem to be less of the larger rocks right where it is. So they picked that spot pretty carefully. And there again, you see the tracks made by the rover. And they're pointing out here, the camera that took these pictures is what they call mass cam. There are two of them actually, and they're zoomable. Now here, they're looking out over the area where the helicopter is going to fly. So it's going to fly out there and come back. And here we get some more views of the ground. And I don't know, I get constantly fascinated when they show these pictures, because these are, I mean, we've seen pictures of the ground on Mars a lot before, but these just seem to be clearer than any. So it just indicates how the cameras have improved. Okay.
Something they can do to get that picture of the rover.
Okay.
They could
Now,
before
as we said, the
put them up there and then superimpose that
flight is probably going to take place somewhere during Saturday night, and NASA, and so, or really more like Sunday morning, and NASA has scheduled a live viewing of the first images that come back from the flight. But it's 3:30 Monday morning, so you've got to be really dedicated if you want to see them as soon as they get back. Now, they'll be available, once they're here, then they'll be available from the NASA website anytime on Monday. So we should be able to see those pictures, at a reasonable time of the day on Monday. They're going to attempt some of the, I think it's a mass cam that can take video. They're going to attempt to get video of the helicopter flying, and they think probably they can do that. They've never, of course, this, I can't think of any other time when they pointed a camera at something on Mars that moved. So we just don't know how the video will turn out, but hopefully it'll be okay. The other thing they're going to try to do, remember the microphones, there are two microphones. They're going to try to record the sound of the helicopter flying. And again, nobody knows how that will work. The big problem, I mean, if they were very close to the helicopter, then we can feel fairly sure that would work, because we've heard, for example, the sound of the rover driving, but they're about 60 feet away. And that, as we said, the atmosphere is extremely thin. And so we just don't have any idea how sound will carry. So we might possibly be able to hear the sound of the helicopter. We just have to wait and see. Now, after each flight, the helicopter will then be given a full day on the ground to recharge its batteries from the solar panel. So if it flies, we'll go ahead and call it, say, Saturday on Mars. If it flies Saturday on Mars, it wouldn't fly again until Monday on Mars. And so, since there's at least a day between each of the test flights, they're going to continue the test flights throughout the end of April and maybe even into the first week of May, just depending on, if they get the helicopter up and it performs well, and they start taking pictures, and that the pictures from the helicopter show something interesting, then they'll probably do additional flights to get more pictures. Okay, now you probably have thought about this, but just an interesting point because of the what an effort NASA made for this particular thing. This is the first flight of a human-designed aircraft on Mars. And we all know, of course, that the first human-designed heavier than air aircraft, not counting balloons and dirigibles, that flew on Earth was when the Wright brothers flew their airplane at Kitty Hawk in North Carolina in 1903. Now, the Wright brothers, you probably know this, but they weren't, they weren't trained engineers. They were bicycle mechanics. They owned a bicycle shop in Ohio, and they had just gotten fascinated with the idea of flying. In the late 1800s, several people in Europe tried to build, without success, heavier than air aircraft and fly them, and they just did not have any luck. But the Wright brothers read about what they were doing, and they thought, wow, it would be really great if we could do this. Well, they did have the bicycle shop, and that meant they had a certain amount of equipment for working on bicycles, and they were able to make use of their equipment to build their own airplane. And what they built it out of was strips of balsa wood, which is, of course, very light wood. And then they used fabric to cover the balsa wood frame. Now, after they made their first successful flight at Kitty Hawk, then they said, wow, okay, that was nifty, but of course, it's not a really practical airplane. We'd like to now build an airplane that would really be worthwhile. But they had a problem here because they were bicycle mechanics. They owned a bike shop. You don't make tons of money doing that. It was obviously going to take a lot more money to build an airplane that would be really practical for flying. But one thing that they did have, because of that first flight, they were famous. The news, this was one of the first events that really got press coverage just about everywhere in the world. And so they realized that since they were famous, that they could use their fame to get some money. So what they did is they took all the fabric off of this airplane they built, and they cut it up into little teeny squares, and they offered them for sale to the public, and people bought them. Everybody who had a reasonable amount of money, it'd be, wow, you get a piece of the first airplane. And so they made a lot of money that enabled them to continue to design and build airplanes. And it turned out that there's a flight museum that bought up a number of these squares of fabric because they said, okay, we're going to be a museum of flight, and this is something from the very first airplane. So he wants on it. So they owned a number of these squares. And so they donated one of their squares to NASA. And NASA took that square and I say they glued it. They may have, I don't know, they may have some other way of attaching it. Somehow or another, that square fabric is attached to the inside of that helicopter. So when this first aircraft flies on Mars, it's going to carry a little piece of the first aircraft to fly on Earth. And NASA, I don't know, they have a real ability to recognize the significance of things and do stuff like this. It just always impresses me that they would think to do something on this order. This is not the first time they've done things like this. Okay, one more thing we want to talk about the rover, and that's one of the instruments on the rover that's already in use, and it's the what we might call the weather station. It's called MEDA, which stands for Mars Environmental Dynamics Analyzer, and it collects a lot of data. Now, it turns out that both the Curiosity rover and the InSight lander also collect weather data, but MEDA is collecting a lot more. It's collecting temperature, relative humidity, barometric pressure, wind speed, wind direction, and solar radiation data. And the first data they collected showed there was a daytime temperature of -4 degrees Fahrenheit and a wind speed of about 22 miles an hour. Now, it's important that this instrument has got the ability to measure wind speed for the helicopter. Because, of course, the helicopter's got to fly in that wind. Now, they tested it here on Earth by using fans to blow wind at it, and they know it's able to fly in a reasonable wind gust. So this 22 miles an hour will not be any kind of problem. But we think from data collected from the other rovers and also from observations made by satellites passing over, that Mars, they're capable, there's storms on Mars that can really blow, but we think maybe wind up on the order of maybe 100 miles an hour. And that would be a problem for the helicopter. So fortunately, we have this weather station, and it's able to detect the wind gusts. And so if it showed a really powerful wind gust, then they would probably just postpone a test flight until the wind died back down again. And then since we now do have 3 different weather stations on Mars at 3 locations, and they're fairly widely separated, we're now capable of collecting weather data from different places on Mars simultaneously. And that's going to give us the first ability to maybe begin to analyze the climate on Mars. Because I don't know, and I haven't really read anything about this. I don't know whether and I don't think anybody knows at this point, if, for example, if there are weather fronts on Mars, would they like move from one weather station to another so that you could actually detect them? We don't know that, but at least we're getting some information on the weather in 3 different locations, and that's a lot more than we used to know about the weather on Mars. Okay, before we go on to the next topic, we have any questions? Okay. Oh, I'm sorry, I forgot. There's some more pictures. This is just another picture, and I know why I put this one here. because you can see there that that lower blade is, at this point, it looks like the top blade is deployed, but the lower one is not yet. And the other thing about this is you get this really sharp shadow here, which shows that even though Mars is about 50% further from the sun than the Earth is, but sunlight's still pretty powerful there because you get this really well-defined shadow of the helicopter. Oh, and then this other thing that I put on, remember on the mars.nasa.gov website, there's a web page you can go to that says, "Where is Perseverance?" Well, it turns out that it's actually making a continuous track of where Perseverance has been. So this actually shows us what it's done since the time it landed. This was like the first drive it made. It went over here, then it turned around, and then it went way over here, down to here, turned around, and came back, and now it's back right here. But you can't tell it here, but the total distance it's traveled is about 1/10 of a mile. So even though it looks like it's really been on a journey, hasn't really gone that far yet. Okay, so now on to our next story. Okay, now I have a confession to make. I thought really hard about doing a story on math because I said, oh my gosh, I don't want to do something and just go right over everybody's head. And, you know, a lot of the math stories I see, they go over my head. And so, you know, it would be way too difficult to try and explain one of those. But I found one where it only involves arithmetic, really. And so I thought, okay, I'm gonna talk about this one. So the headline here says, mathematicians find a new class of prime numbers. And over here, this picture is showing us the beginnings of the sequence of prime numbers, 2, 3, 5, 7, 11, and so on. This is all the prime numbers between 1 and 100. Remember what a prime number is. It's defined to be a number which is greater than 1 and can only be divided by itself and 1. Okay, so it doesn't, so if we go back here, if we take, like, say, the number 7, say, in this list, you can't divide 7 by any number except 1 and 7. Likewise 11, likewise 5, and so on. So they're all primes. Now, that definition deliberately excludes 1 because it says it's a number greater than 1. And that's intentional. It turns out, I mean, because if you look at 1, well, it can only be divided by itself, and but of course it's also divisible by 1. So you can kind of say, well, that kind of fits, but we don't want it to. And the reason we don't want it to is a lot of the things that turn out to be true about primes would not be true if we considered 1 to be a prime. So again, here's just the first few prime numbers listed. Now, prime numbers are studied in an area of math that's called number theory. And more generally, number theory is the area of math where you study the properties of whole numbers. Prime numbers have been studied for around 2,500 years. Many of the results that we know about prime numbers were actually developed by the ancient Greek mathematician Euclid. And if you probably have heard of Euclid, most people who are our age, if you took plane geometry, it was you heard about Euclid. Some of us may have even used as your textbook the book Euclid wrote called The Elements. But it's interesting that that's actually a multi-volume book. And I forget how many volumes off the top of my head. The first few volumes are about geometry, but the last volume is actually about number theory. And one of the results that Euclid stated and proved there is that there is no largest prime number. That is, the sequence of prime numbers just goes on and never stops. And the proof he gave is a very elegant form of what we call a proof by contradiction. And I'm going to run through this just because it is just a very nifty example. He starts out by saying, okay, suppose there is a largest prime number, and I'll call it P. And he said, now I'm going to make a new number. And the way I'm going to make that number is I'm going to start with 2, and I'm going to multiply by each of the other prime numbers I know. So starting with 2, 3, 5, 7, 11, keep going, until I hit that largest prime P. So now I have multiplied together all the prime numbers, and then I'm going to take the number I got and I'm going to add 1 to it. So this number Q is the product of all the prime numbers plus 1. Okay. So obviously, Q is a number that's bigger than P because it's the product that includes P and a bunch of other numbers, then has 1 added to it. However, Q is also a prime number. How do we know that? Well, what do we say a prime number was? That it was divisible only by itself and 1. If we tried to divide Q by any of those smaller prime numbers, we could not, because we have this 1 added on to it right there, the plus 1. So it always get a remainder of 1. So now we found a number, which is a prime number, but it's bigger than P. But our assumption was that P was the biggest number. So we've reached a contradiction, and the only way out is to say, well, our assumption must be wrong. There is no biggest prime number. So that's Euclid's proof that the prime numbers just keep going. There's no biggest one. Okay, so it turns out that the study of prime numbers is really interesting because there are many problems that we can state in such a way that, anybody who knows how to do arithmetic can understand what we're talking about, but that it's just difficult, if not impossible, to prove them. And I'm going to give you one such example. This goes back to 1742. A German mathematician named Christian Goldbach said that he thought that every even number greater than 2 would be the sum of 2 primes. And so this thing is now called the Goldbach Conjecture. And so what it's saying is, if we take an even number bigger than 2, if we took 4, well, 4 is 2 plus 2, and 2 is a prime. So 4 is the sum of 2 primes. Likewise, 6 could be written as 3 plus 3, and 3 is a prime, so it's the sum of 2 primes. And 8 is 5 plus 3, and 5 and 3 are both primes. So starting out with those examples, it seems to be correct. And if you keep trying, you'll find that, like let's take a bigger even number. Let's take 20. Okay. Well, 20 is the sum of 7 and 13, and they're both primes. You can keep going and going and going. And every even number that anyone's ever tried so far, they have managed to find a couple of primes that will add up to it. So nobody's ever found an even number which is not the sum of two primes. But people have also tried to prove that in general, that's a true statement, that regardless of which prime number you took, you could always, regardless of which even number you took, you could always find two prime numbers to add together and give you that number. And nobody has ever been able to prove that. There's still mathematicians today who are working, trying to prove that. So it's been going on for over 300 years without anybody successfully proving it. So the research we're going to look at today has to do with an even stranger property of prime numbers. And to me, the weirdest thing about this is how this first guy ever came up with this idea. I don't know how people do this. This was a mathematician named Murray Clampkin, and he wrote for Mathematics magazine, which is a mathematics journal that's really like a lot of high school math teachers take it. It's not an advanced journal at all, but it has some awfully interesting problems in it. And so writing in Mathematics magazine, this guy Murray Clampkin said, I think there is a new class of prime numbers, and I'm going to call them digitally delicate prime numbers. And here's what that means. If you write out the representation of the prime number in terms of all its digits, like, let me take a 97, for example, 9 and 7. He said a prime number is digitally delicate if you took one of those digits and changed it to any other digit. So the digit you chose is some number between 0 and 9, and you change it to any other number beside the one that it currently is. If by doing that, the new number you get isn't a prime number anymore, then he says the original prime is what we call digitally delicate, meaning that if we modify any digit, it loses its property of being a prime. So he said, that's my definition. Now he said, are there any? He said, so in effect, he's invented a class of prime numbers, but he hasn't found any of them yet. Well, the first thing that happened, and it happened almost right away, there was a famous mathematician. He's passed away, I think, around 1998, somewhere in there. But at this time, he was still very active. A guy named Paul Erdős. He was a Hungarian, so that's why his name is pronounced a little differently than you might expect. In the very next edition of the magazine, he produced a proof that not only did there have to be such primes, but there had to be infinitely many such primes. Okay, but that still didn't give an example of such a prime number, but it said they had to be there. And knowing they had to be there, other mathematicians started looking for them, and they found them. For example, the number 294001, the number 505477, 5041401. These are all numbers. If you take any, like if I take this one, if I pick that 4, for example, and change it to a 5, the new number would not be a prime number. If I took the 0 and changed it to a 7, the new number would not be a prime number. If I modified any one digit there, then the number I got would not be prime. And people have found many, we know there are infinitely many, so you got to be able to find ones that are much bigger than this. And people have found ones that have up to 2,000 digits. So imagine that. You have a number that's 2,000 digits long. It's a prime number. If you pick any one of its digits and change its value, you're guaranteed that the new number will not be a prime number. And that's where it starts to seem like, whoa, this is weird. Because if you have 2,000 digits, you could pick any one of those 2,000 and you could change it to anything else. So that means that you could change that to any one of 9 different things. It just looks like it's just astounding that you always get a number that's not a prime number. Okay, now the new research that we're talking about today was done by a couple of mathematicians at the University of South Carolina. That's another reason that I got interested in it. It's some almost local people who did it. And they have come up with a new class of what they call widely digitally delegate prime numbers. And what they mean is numbers that satisfy that previous definition of being digitally delegate, but also satisfy an additional condition, which means that you can put a string of zeros in front of the prime number. So you start out with 0, 0, 0, 0, or however many zeros you want, and then let it go on from there. And it still has that same property. That is that you could change any one of those zeros you put in front to a non-zero number, and the number you got would not be a prime. So if we took, for example, this number 294,001, and let's say we put 3 zeros in front of it. Now I could pick any one of those zeros, and I could change it to any number between, it's got to change it from 0, so that'd be something between 1 and 9. And the number that I came up with was guaranteed not to be a prime number. And so once they had made this definition, then they went on to prove that there must be infinitely many such numbers. Now you might be curious, because just like the original proof about digitally delegate, they didn't actually exhibit any, and nobody has up till right now. But for example, if we took this one right here that I came up with, you might say, well, maybe it's digitally delegate, but it isn't. I know it isn't, because if you change that first 0 to a 6, you get this number, 600294001. That is a prime number. How do I know that? Well, if you go out on the internet, you can find these prime calculating tools where you can give them a number, and they will either give you the factors of the number or they'll say it's prime. And so I went to the prime calculator, and actually what I did is I started with 1. I started with 100294001, and it's not a prime. I did 2, 0, 0, 0, so on. It's not a prime. I kept going, but when I hit 6, it turns out it's a prime. So this number with 3 zeros in front of it is not a widely digitally delegate prime. And so far, as I know, we don't know any, but somebody will come up with one soon, I promise you, because it's been shown that they exist. And so there are people out there looking right now. Okay, I'm going to ask the obvious question, and then I'll let you ask any questions you want. Obvious question, what's this good for? And the answer is, I don't know that it's good for anything. It just struck me as interesting and intriguing. Now, I don't mean to say that prime numbers don't have a very practical use. Back when we were talking about information theory, And we talked about encryption, how you can take some computer data and encrypt it so somebody else can't tell what it really is. We mentioned there that encryption techniques depend on being able to find large prime numbers and multiplying them together. And so prime numbers themselves are important. And it turns out, we said there are a lot of difficult problems to do with prime numbers. A really difficult one is just finding them. There are lots of them known, but it's really hard to find new ones. And one thing that's helpful in trying to find new ones is knowing more about the properties of prime numbers, because that sort of tells you where to look. But other than that, I can't say that there's any value to this thing except just purely for it's a nifty piece of math. Okay, any questions about this? Okay, so we have one more story for today. And since we talked about atomic clocks last week, I thought this was very good to have this one come up because it has to do with new types of atomic clocks being built. And it gives us a chance to talk a little bit about how atomic clocks work. So since 1968, the official definition of a second has been the time it takes for 9,192,631,770 quantum transitions of the element cesium to occur. Okay. And what that means is the element cesium has a couple of energy levels, and quantum theory tells us that it will transition between those energy levels with a certain probability. And if we have a lot of cesium atoms, then if we can figure out some way to get them in one value of the quantum, in the high value of the quantum state, then we can predict how long it will take for them to drop down into the lower value of the quantum state. And that's what is behind the building of an atomic clock. So there are a lot of different ways, and we're going to talk about just one of them. And this is one in which you take a cloud of cesium atoms and you heat them in an oven, and then you send the heated atoms through a magnetic field. And let's just, we said there's two quantum states. We don't really want to get into, what's involved in the atom in those two states. We just want to give them names so we can tell them apart. So we'll call them state A and state B. And that first magnetic field removes all the state B atoms from this heated cloud of cesium atoms. So now you've got only state A atoms, and they get sent into a device called a cavity resonator. And in that resonator, we use a microwave beam, which is tuned to exactly 9,192,631,770 oscillations per second. And that excites the cesium atoms, and so that some of those in state A get pushed up into state B. And now they go through a second magnetic field, and that one takes out all of state A atoms. So what we have left now is atoms that are guaranteed to be only in state B. And we now have a way to count them, and we're not going to go into how that's done because it's very technical. But what's important is this. Quantum mechanics tells us how to predict what we should get in our count. And if the actual count we get when we count them is anything different from that, it means that our microwave frequency has gotten a little bit off. And so we tune the microwave frequency until this count that we get exactly agrees with the quantum prediction. When it does that, then we know that we can use that microwave frequency as our clock signal. And so that's what is used as the standard for the clock. And here we got a little diagram that sort of shows how this thing works. Here's our oven. We heat the cesium atoms. They go through the first magnet. And so that puts them atoms only in state A into the resonator. Then the microwaves turn some of the state A atoms into state B atoms. So the color changes from blue to orange. They go through a second magnetic field that drops out any remaining state A atoms, and only state B atoms go into the detector to get counted. And if that count is off in any way, then the microwave frequency is adjusted until the count comes up with the correct value. Okay. So the current atomic clock, if whenever you're listening to radio, and I don't think they even do this anymore, but they used to do, at the tone, the time will be exactly. What they're doing then is they're giving you the value from the atomic clock at the National Institute of Standards and Technology, which is in Boulder, Colorado. It used to be called National Bureau of Standards. Now, it's somewhat more accurate, more complex than the one we described, but basically works in the same way. How accurate is it? It's accurate to 1 second in 100 million years. So that's pretty accurate. However, the scientists at the National Institute of Standards and Technology, and some people who work with them at the University of Colorado, which is also in Boulder, are working on new atomic clock designs. And these new clocks would use quantum transitions from 3 other elements: aluminum, strontium, and I never know how to pronounce this, ytterbium maybe? That's a rare earth element. And also, instead of using microwaves, they use visible light to affect the quantum state changes in the clocks. Now, the use of visible light is important because visible light has higher frequency than microwaves do. And so that means that you can design clocks that are more accurate. In fact, they estimate that the clocks that they're building now will be accurate to 1 second in 15 billion years. Now, as we've discussed a number of times, astronomers think the universe is 13.7 billion years old. So what this means is, if somebody had an atomic clock like this and started it at the time of the Big Bang and it had run ever since up till today, it would still be accurate to within 1 second. And that's just mind-boggling to think can be that accurate. Now, you might also, again, you might wonder, do we really need clocks that are that accurate? But we pointed out last time that atomic clocks can be important in doing a lot of physics research. We saw last time in measuring and coming up with the image of the black hole, they used atomic clocks to synchronize the data from the various radio telescopes. And their results have a tiny bit of potential error in them because the atomic clocks they use are only these, accurate to 1 second in 100 million years. So if they had had the new kind of clock that's being built now, they could have reduced that error factor by a factor of up to 1 million, which is a real drop in the potential error due to your time measurement being incorrect. Okay, so that's the end of that story. We have any questions about it?
Bill?
Yes.
Yeah, where did the link from the original cesium number come from that says that's 1 second?
It's what we define, that up till that point, and I honestly don't. There was some intermediate standard, a long time ago. The second was defined to be there was a very delicately balanced pendulum that was kept in a vacuum chamber, and it was defined to be the length of one swing of that pendulum. But then I know that was replaced later on by some other standard. But at any rate, whenever they change standards, they first have to do experiments and verify, basically find out. What they did is they took the existing standard for a second and they said, okay, how many cesium transitions take place in this interval? So they use the existing standard clock. Now you might say, well, that wouldn't be any better because they're just getting the same thing. But they actually do that over and over and over again. They don't do it just once. They do it thousands and thousands of times. And in that way, they can establish precisely a number that's a better representation for the second than what the old standard was. And likewise, when they adopt one of these new clocks, they'll go through the same process. They'll basically calibrate the new clock by the cesium clock.
Good. Okay. So 1001 isn't accurate. I use 1001 for a second.
Oh yeah, well, that is, as far as I know, 1001 is, in terms of, human accuracy, if you're sitting around, that's pretty. What we're talking about here is, if I want to tell you when 15 seconds is up, I don't count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 up to 15. I count 1001, 1002, 1003, 1004 up to 1015. And that's, that's okay. I mean, that's certainly the best that people can do without depending on something else.
Thank you.
That wouldn't
Any other
necessarily
question?
work too well in other languages, though. If you try to use German or some other thing.
That's true. Yeah, and I'm sure they must do something else in German to estimate seconds, but I don't know what it is.
But I do have
I
another
imagine
question. Bill, I do have another question.
Yes.
This is also sort of irrelevant, but in the primordial plasma soup that existed after the Big Bang, there were no elements, including cesium and ytterbium or whatever it is, and so forth.
Right.
When they did develop, could their quantum transition values have changed after that? I don't know.
Yeah, okay, and I don't either. That's a very good question. Yeah. This is one of those things that, it's probably unknowable.
Yeah.
There's probably no practical way to ever figure out for sure if that's remained what it. I mean, it's just like, there's a question: has the speed of light always been what we measure it now? You can't answer that. We can't go back and measure it way back.
Yeah.
All we can say is whenever we measure it now, we seem to get the same thing.
Just a curiosity.
Yeah.
Thank you.
Any other questions?
Yes,
Okay, well,
did you,
yeah.
I have a question.
Yeah.
In reading this, did you ever stumble across this, the biggest, the longest prime number? Do you know?
Yes. The biggest prime number known now, and I can't quote it off the top of my head, but it would take me several days to tell you the number because it's several million digits long. It turns out that there's a formula that you can use that to calculate numbers and then check and see if they're prime. And it's not a very good formula because at this point it has only produced 51 total prime numbers. But it has given us there's two values to it. It's easily adapted to the computer, so you can write a program that will test the formula, and eventually that's the way they find these prime numbers, is they just keep throwing numbers at it and testing, and eventually they hit one. In fact, I think it was last year, the 51st prime number was found. And it's like I said, millions of digits long. But if you want to find out about that, the man who developed that formula was named Mersenne. He was French, Mersenne. So if you do a web search for Mersenne primes, then you can find out exactly what is the currently biggest prime number known.
Concerning prime numbers and quantum computing, I'll bet you there are a lot of quantum computer people that are looking into some of these problems dealing with prime numbers. And, it would seem that they'd be able to find some more using computing.
That's certainly true. I mean, the thing about this current formula that I said is used is, I think last year, 2019, I think they found one. Just going by what's happened in the past, I mean, there are computers all over the world right now as we speak, grinding away on this formula, trying to find another prime number. It will probably be 10 years before another one is found. Okay. But quantum computers would be able to do that really quickly. So you're right. It really is a very, very hot topic in that area when we get our practical quantum computer.
Yeah, another comical thing was reading a book, and they were talking about right now, people cannot just take up two arbitrary floating point numbers and multiply them in their head. But they think that possibly in some evolution, some new type of world, that there would be beings that could do something like that. Just take a floating point of maybe 15 digits or something like that, multiply two of them together. And, human beings are limited. We can only multiply numbers, certain sizes. Anyway, it's cute to think that way.
Okay, well, thank you everyone for coming today. Next week, hopefully, we'll have pictures of the helicopter flying, maybe even video of the helicopter flying. So I hope you'll all come back and join us then. So thanks, and
Thanks, Bill.
Okay,
see
thanks.
you later.
Yeah.
Thank you.
Bye.
Thanks. Bye.
Bye-bye.